Hey, this is Charlie Thompson, and this is the Lab 12 Tectonics How to Calculate Rates of Movement video. So, math. In this lab, we're going to calculate the rates of movement along plate boundaries, and we want the answer in centimeters per year to 1 decimal place. We're going to measure the length in centimeters, or you can measure it in kilometers and convert to centimeters. I'm going to recommend that you measure it in kilometers and convert it to centimeters. Age is given in millions of years for the Hawaiian Islands. Age is given in years. So I mentioned units, and this really threw off students previously that when you're looking at the Hawaiian Island problems, the ages of the islands are given in millions of years, and then when we start looking at the San Andreas Fault around Wallace Creek, the ages of those are just years. So you got to pay attention to the units. Some of the years are millions of years. Some of the years are just years, like 3,400. So values and units, what the fuck? Values and units are going to be super important to pay attention to. So rates of movement, the distance in time in centimeters per year, distance moved per time. So for example, in the Hawaiian Islands, one of the things we're going to be doing is looking at the distance from island to island and seeing how long it's taken the plate to move that distance. So we know that it's 321.6 kilometers measured from Kimai to Abbott, from Kimai Seamount to Abbott Seamount. And we know that Kimai is 47.9 million years old. So values and units, to go over that again, 321.6 is the value. Kilometers are the units. So 47.9 million years, 47.9 is the value. The units, in this case, are millions of years. MY is the abbreviation for millions of years. So Kimai is 47.9 million years old. There's Kimai, there's Abbott. So I'm going to ask you to calculate how long it took the plate to move, the distance from Miji Seamount to Kimi Seamount. I'm also going to ask Abbott to Laysan Island, and then Laysan to Loihi. So this is the youngest part of the plate, and it's getting older and older, about 40 million years old, about 80 million years old. So we're going to be comparing the rates of movement with the oldest part of the plate, with the middle-aged part of the plate, with the youngest part of the plate. And as an example, I just wanted to show you if we wanted to figure out how long it would take to move the plate to move the distance from Kimai Seamount to Abbott Seamount. So we need to know what the difference is in age, and then need to know the distance. So we need to know the distance and then divide that. So what do we know? Distance divided by time in centimeters per year is what we want to end up with. So 321.6 kilometers is the kilometers. Kimai is 47.9 million years old. Abbott is 38.7 million years old. So 9.2 million years. That's the difference in age. So 9.2 is the value. And 9.2 is the value, and millions of years are the units. So we know that it took that plate moved 321.6 kilometers in 9.2 million years. So rather than kilometers to millions of years, we want the answer in centimeters per year. So 321.6 kilometers in 9.2 million years. I'm going to recommend that you use this, unitconverters.net. So I just dropped in the number 321.6 kilometers and then told it convert it to centimeters. I would suggest copying that, like right-click, copy, and then I would paste it, and I would put in the commas so that I don't get like 100,000 confused with a million, or 10 million confused with 1 million. So you don't end up having your answer be off by a factor of 10, or 1,000, or 100, or 100,000, or whatever mismatch in units happens. So 321.6 kilometers, 32,160,000 centimeters. So we've got 32.2 million centimeters over 9.2 million years. If we divide 32.2 by 9.2, we end up with 3.5. So we get a speed of 3.5 centimeters per year. I didn't have to round with this one. It just comes out to 3.5 centimeters per year, but all of the rates of movement I want rounded to 1 centimeter. That's it. Time to move a given distance. We want the distance per time in centimeters per year. How long for San Francisco to move to Seattle? So San Francisco is on the Pacific Plate, and the Pacific Plate is moving to the northwest. The distance is 1,091.8 kilometers. There are just some convenient numbers for you. 100,000 centimeters in 1 kilometer. So the distance is, and again, I would just take that and drop it into the unit converter's website, and you'd end up with 109,180,000 centimeters. Using a speed that I'm just giving for this problem, 6.9 centimeters per year, movement average over the San Andreas Fault. Different parts of the fault have different rates of speed, so don't use this later. I'm just using this for this example. The other problems will tell you what rate to use. So the average 6.9 centimeters per year. Here we've got San Francisco to Seattle measured at 1,091.82 kilometers. So we've got the distance now in centimeters. We're going to divide that by 6.9, and we get 15,823,188.4 years for San Francisco to move up to be at the same latitude as Seattle. Some handy conversions. There are 10 millimeters in a centimeter. 1 meter has 100 centimeters. Kilometer has 1,000 meters. 1 kilometer has 100,000 centimeters. 2.54 centimeters equal 1 inch. And I'm going to ask you to convert over some of the rates into inches because not everybody speaks metric. And there's the unitconverters.net website. I'll put that in the link to the quizzes as well. And that's it for the Plate Tectonics How to Calculate Rates of Movement Lab. If you have any questions, please come to Zoom. Ask me questions. I'd love to help you get this straightened out so that you can just breeze through the lab. That's it, and good luck.